Hello physics students. This video is all about tangential and centripetal acceleration. Again, we're looking at rotational motion, and we're going to talk about tangential speed, tangential acceleration, centripetal acceleration, and total acceleration. So let's start by looking at tangential speed. It really is just what the name implies. It is the instantaneous linear speed of an object directed along the tangent to the object's circular path. It's a lot of words, but what does that mean? Let's pretend that there is a ball being swung about, being held by a string, and it's being swung about in this circle. At any moment, let's say at this particular moment, that ball has an instantaneous linear speed in this direction. It is tangent to the object's circular path. Again, let's think about our horses on the carousel. Remember that because it's a rigid object, any two horses attached to the carousel have the same angular speed and angular acceleration, regardless of their distances from the axis of rotation. If, however, like in this example, the two horses are at different distances from the center, from the axis of rotation, right here, then they are going to have different tangential speeds. And that is obvious as we can draw this. The tangential speed for the outside horse is going to be different than the tangential speed from the inside horse. V sub t stands for the tangential speed. So we could ask this question: if the horses were released from the carousel, kind of like on the Mary Poppins movie, they come alive and they're released, which one is going to travel farther before hitting the ground? Well, the outer horse would travel farther. It has a higher tangential speed. This is obvious because in our little diagram, it has a longer vector for its velocity. But also you know that the horse on the outside is going to have to travel the same angular displacement during the same amount of time as the horse on the inside. And to achieve this, the horse on the outside must travel a greater distance, or greater delta S, or must travel a greater arc length than the horse on the inside. So an object that is further away from the axis of rotation is going to travel at a higher tangential speed around the circular path, delta S, than the object on the inside. So how can we calculate tangential speed? Well, let's take some things that we already know. We know that the equation for angular displacement right here, and if we take that equation and we divide both sides by the time it takes to travel whatever the delta S distance is, we end up getting delta t on the bottom of both sides of the equation. And this term should look very familiar to you. Change in angular displacement over change in time is our average angular speed. So we can substitute this in for that term. And we also know that delta S is a linear distance. So when we have delta S divided by delta t, that's linear speed along an arc length. And if delta t is really, really short, then delta S is so small that it is nearly tangent to the circle. Therefore, the speed is the tangential speed. So we can rewrite our tangential speed equation right here. The tangential speed, right there, is equal to the distance from the axis, r, times the angular speed, right there, omega. So omega in this case is the instantaneous angular speed rather than the average angular speed because the time interval is so short. And also, this equation is only valid if omega is measured in radians per unit of time. Let's try an example where we use this equation. And let's say we have a CD, and the radius of that is 0.0600 meters. we have, say, a little microbe, a speck of something riding on the disk's rim at the edge. It has a tangential speed that should say speed of 1.88 meters per second. What is the disk's angular speed? So I'm going to write down what I know. I know the radius. I've been given that. I also know the tangential speed. So there's the tangential speed, 1.88 meters per second. And I want to know the disk's angular speed. I can use the equation for my tangential speed that we just learned, and now I can plug values into that equation. And when I do the math, I will see that I get for omega 31.3 inverse seconds. It's actually radians. Remember, radians are pure number. So it's 31.3 radians per second. Now let's take a look at tangential acceleration. We know that on this carousel, if the carousel speeds up, these horses on it experience angular acceleration, which is simply instantaneous linear acceleration of an object directed along the tangent to the object's circular path. So very similar to our idea of acceleration being the change in velocity over the change in time, because we're looking at that linear acceleration of the object directed along the tangent. So how can we find tangential acceleration? I'm going to start by using our equation for tangential velocity that we just learned right here, and we can simply divide by the time interval on both sides of the equation. When we do that, we get this equation, and if the time interval, delta t, is very, very small, then the left side of this equation gives us the tangential acceleration of that point. The angular speed divided by the time interval on the right side, right here, is the angular acceleration, alpha. So we get the tangential acceleration of a point on a rotating object given by this relationship right here. Again, the angular acceleration in this equation refers to the instantaneous angular acceleration. And again, this equation is only valid when the angular acceleration is expressed in units of radians per second, or radians per second squared. Let's try an example using our equation that we just learned about. If the spinning ride at an amusement park has an angular acceleration of 0.50 radians per second squared, how far away from the center of the ride is a rider who has a tangential acceleration of 3.3 meters per second squared? I'm going to write down what I know. I know the angular acceleration is 0.50 radians per second squared, and I know my tangential acceleration is 3.3 meters per second squared. I'm being asked to find how far away from the center of the ride, so I would like to find r. I can use my equation for tangential acceleration that I just learned, and I'm going to plug the values into that equation. I plug those values in, and then I rearrange the equation just to show you how the units are going to cancel out. My per second squareds cancel out in both cases. Radians doesn't have any meaning to us. It is because it is a pure number, right? Radians are a pure number. So I'm really only left with meters, and my answer then is r equals 6.6 meters, and that is the distance from the center of the ride where my person is sitting, where the rider is sitting. Now we're going to take a look at something called centripetal acceleration. And to do this, let's imagine a car going around in a circular path, and it's traveling at a constant speed of 25 miles per hour. So here our car is going around in this circle. Does it have acceleration? Well, remember, acceleration equals the change in velocity over the change in time. I can expand that to this equation here. We know that velocity is a vector, so there are two ways acceleration could be produced here: a change in the magnitude of the velocity or the change in the direction of the velocity. For a car moving around in a circular path with constant speed, the acceleration is due to a change in direction. An acceleration of this type is called centripetal acceleration. It's directed toward the center of a circular path, and this is the equation that we can use to talk about centripetal acceleration. The C stands for centripetal acceleration. So let's look over here at our drawing. If v1 is the initial velocity and v2 is the final velocity, we can see that they differ only in their directions. Their magnitudes would be the same, and they're just going a different direction. We know that the change in velocity is equal to the final velocity minus the initial velocity, and we can determine that graphically over here. If I simply redraw the initial velocity and the final velocity, I can determine delta v. Note that if we have a delta t that is very, very small, approaching 0, the final velocity will be almost parallel to the initial velocity because they will be very, very close together. And delta v will end up being nearly perpendicular to them, pointing toward the center of the circle. You could see how that would happen. This means acceleration will also be directed toward the center of the circle because it's in the direction of delta v. So here we have our centripetal acceleration formula. And the interesting thing, we can also derive another equation from it because we know this relationship here. We can substitute these variables into this equation, and then we can reduce that equation a little bit. The r's cancel, and we end up with centripetal acceleration equals r times omega squared, which is right here. So we can use either of these for centripetal acceleration, this being the angular speed squared, r being the distance from the axis, and a sub c is centripetal acceleration. Let's do a sample problem. Let's say we have a test car moving at a constant speed around a circular track. The car is 48.2 meters away from the track's center. It has a centripetal acceleration of 8.05 meters per second squared. What is its tangential speed? Let me write down the things I know. These are the things I know. I want to find the tangential speed, and correct units are used all above, so I can use my equation for centripetal acceleration. So I plug my values in for centripetal acceleration and for the distance from the center, and I now can solve for my tangential speed. My tangential speed is 19.7 meters per second, and don't forget that v sub t is squared, so I'll have to take the square root of the product of those two numbers. Last but not least, let's look at the difference between tangential acceleration and centripetal acceleration. They are not the same thing. If we think about our car example where a car is moving along a circular track, it has a centripetal component of acceleration because its direction that it's traveling, and hence the direction of its velocity, is continually changing. If the car's speed is increasing or decreasing, the car also has a tangential component of acceleration. So we can think about the difference as the tangential component of acceleration is due to changing speed, so it will affect the magnitude. The centripetal component of acceleration is due to the changing direction. When both components of acceleration exist simultaneously, we can find the total acceleration using the Pythagorean theorem because they are perpendicular to each other. That's because the tangential component of acceleration will be tangent to the circular path, and the centripetal component of acceleration will be pointing inward, and these will be perpendicular to each other. Therefore, the magnitude can be determined using the Pythagorean theorem, and then the direction can also be determined using the tangent function. If we were to draw this on our graph over here, we would actually need to draw the tangential acceleration first, and then the centripetal acceleration second, we could then look at it as the resultant of those two vectors would be that line right there. And these would obviously be perpendicular to each other. Advanced ideas make up some problems regarding magnitude and direction of an object's total acceleration. Using these ideas right above there, you can try for your own problems, and I look forward to seeing you in class.